The rectangular coordinate system is a way to say where something is in a two-dimensional plane. See, if I were to walk over here somewhere and put a dot and ask you, hey, where's that dot at? It's a silly sounding question because we're looking at it, it's right there. But considering we have no way to reference where it is, you can't really say other than, hey, it's right there, where is it? To reference where something is, we always refer to somewhere else. Like if I said, where's that dot at? You could say it was 2 feet away from the plus, kind of up that way. You see what I mean? You'd say it's close to that thing. So the way that we're going to do this to say where things are in a two-dimensional plane is use something called the rectangular coordinate system. Now, all the rectangular coordinate system is, it's 2 number lines. And then another one put perpendicular to it. Let's go right through there. All right, so we have 2 what we call axes here, and they're number lines, and they're intersecting where both number lines are 0. So I'm not going to put the 0 right there. So for the horizontal number line, it'd be like 1, 2, 3, -1, -2, -3. For the vertical one, it'd be like 1, 2, 3, and down is -1, -2, -3. Now to say where something is, I'm going to go ahead and put another dot up here. What we're going to do is we're going to break down where it is into 2 directions. We're going to say how far we have to walk left and right and how far we have to walk up and down to get to there. Now to make sure that we all have the same directions, we're all going to make sure we start at the same point. The point in the middle where both number lines meet, this is called our origin. Now this is where we're going to originate from. So from here, we're going to say how far we move left or right and how far we move up and down. Now, we want to always give our directions the same way. The way that we do this is we give it as an ordered pair. Basically, just a fancy way of saying 2 pieces of information. Now, generically speaking, we generally name the left-right direction or the horizontal direction as the x direction or the x-axis. And the vertical or up and down direction is the y direction, the y-axis. So our ordered pair is going to contain a how much do we move in the x direction and how much we move in the y direction component. So an ordered pair is always given as the x direction first, comma, the y direction next. So for this point right here, notice we started our origin, we take 1, 2, 3 steps in the x direction, and 1, 2 steps in the y direction. So we say that that is the point 3, 2. Now don't get confused. There are 2 pieces of information here, but that's not 2 points. Those 2 pieces of information represent 1 point up here. So if we were to put, say, a point right here, how would we get to this? Well, starting at our origin, we'd move -2 in the x direction, comma, and 1 in the y direction. All right, so you can see that just gives us direction, time on how to move places. Let's see, I don't know, let's put one more up here, just kind of see there. What would this point be? That's -3 in the x direction, also -3 in the y direction. So by looking at this, we can see that it's a very easy way to say where a point is in a 2-dimensional plane. Now for a few things in our future, notice that these 2 number lines break the board or the plane up into 4 different regions. They're called quadrants, and we label them with Roman numerals 1, 2, 3, and 4. You can always tell what quadrant a point is just by looking at the signs of the values. Notice everything here in the first quadrant would have a positive x value and a positive y value. So all the points up there would always be a positive and a positive. In our second quadrant over here, all the x's are negative, but all the y's are positive. In the third quadrant, it would be negative, negative. And in our fourth quadrant here, the x is positive, but the y is negative. Now, it doesn't come into play very much right now, but in our future, we're going to see that that's very helpful to know what quadrant a point is just by looking at it. So from now on, we should always be able to plot a point. So I'm going to give you a few points here. Let's see if I gave you the point. All right, I want you to pause the video, draw yourself a rectangular coordinate system, and see if you can plot these 5 points for me. And we'll see how to label them when you get back. So go ahead and pause and plot those points, please. All right, so let's see if you're back. So if we were told to plot these points, the very first thing we're going to do is draw a rectangular coordinate system. Now you don't need graph paper for this, just sketching a quick little coordinate system like here is really all you need. Remember, the horizontal direction is our X direction, the vertical direction is our Y direction. Now just for neatness, especially when you're drawing on your own paper, you may want to leave off the numbers because it gets pretty crowded when you do that. So most of the time when you see me draw this, I'm not going to label the axes, but we know they both meet where they're both zeros, and we know it's the positive, negative, and negative. All right, so the point 1, 3 says starting at our origin, right, I'm going to move 1 step in the X direction, 3 steps in the Y direction. So that's our point 1, 3. So generally if they tell you to label, all they mean is either write the point next to it like this, or sometimes they'll give you a letter for this, like this was the point A, so you put A next to it. Well, let's try the next one. Next one would be -4, 2. So that says move -4 in the X direction, 2 in the Y direction, so -4, 2. 0 in the X direction, so I'm not moving left or right at all, but I'm going up 6, so that would be the point 0, 6. 3, -1, it says move 3 in the X direction, 1 in the Y direction, -1 in the Y direction. That gives us 3, -1. And our last point here, we have 5, 0, so it says move 5 in the X direction, so we need to add one more there. 5 in the X direction, none in the Y direction, so that's the point 5, 0. All right, we're going to be plotting points, well, for the rest of our math career, so make sure you understand the concept of it. Let's take a look at one more idea. We'll see one place that points can be useful. All right, we're going to take a look at linear equations in 2 variables. Now we've already taken a look at linear equations in 1 variable so far, but what does it look like when we have 2? Well, generically speaking, it looks something like this. By the way, this is called standard form when it's written like this. Now here's where some of the confusion comes in, and understandable confusion, because I just said this is a linear equation. Well, linear means what? The highest power is 1. That seems okay. It's an equation because it has an equal sign. But I said in 2 variables. If I were to ask you how many variables up here, a very valid answer would be 5, right? Because a variable is just a letter and we have 5 different letters up here. So why did I say we only have 2 variables? Well, it's kind of a naming convention that we use in math. If you see letters from the beginning of the alphabet, like A, B, C, D, E, generally when you actually see one of those equations, those are going to be replaced with numbers. If you see letters from the other end of the alphabet, W, X, Y, Z, those generally stay variables. So here, the A, B's, and C's are going to be replaced with numbers, but the X's and Y's are going to stay the same. Quick little example of this might be 2x plus 3y is equal to 4. Okay, now notice this is an equation just like any other equation, which means it has solutions. Now the only difference here with compared to our linear equation with 1 variable, we only needed a value for 1 letter, right? If we had 2x plus 3 is equal to 4, we only need a value for x to have a solution to this. However, to have a solution to this, we're going to need 2 values. So we're going to need a value for x and a value for y, which ties in nicely to the points that we just learned, because a point has an x value and a y value. So let's take a look at a simple equation. Let's go x plus y is equal to 4. And I ask you a simple question. Is the point 1, 3 a solution? Now remember, when you're given a point, the first value is an x value, the second value is a y value. And how do we always check to see if something's a solution? Well, you plug it into the original equation and see if it gives you a true statement. So here's my original equation. So everywhere there's an x, I'm going to put a 1, and everywhere there's a y, I'm going to put a 3. So I end up with 1 plus 3 is equal to 4. Well, that's true, right? 1 plus 3 is 4, so 1, 3 is a solution to that equation. Now here's where we start seeing one of the biggest differences that we have with linear equations with one variable, right? If we had x plus 2 equals 3, generally a linear equation with one variable, if it has a solution, it only had one solution. However, are there more solutions to this equation? Now, without actually knowing how to solve and get solutions here, you can easily see that, of course, 3, 1 would also be a solution, right? Because 3 plus 1 is 4. 2, 2 would be a solution, right? Because 2 plus 2 is 4. So the question is, we've already found several solutions. How many solutions are there to this? Well, there's actually an infinite number of solutions. I can keep doing this all day. Pick any two numbers that add up to be 4. How about 5 and negative 1? Right, because 5 plus negative 1 is still 4. You could use fractions, you could use decimals. Anything that adds up to 4 would work for this. That's tricky because that means that every equation we deal with is going to have an infinite number of solutions. But does that mean that every point is a solution? Well, the answer to that is no. So if I were to take the point negative 2, negative 3, that would be negative 2 plus negative 3. That is not 4. Okay, so we end up with a very interesting situation here. We have an equation that has an infinite number of solutions, but not everything is a solution. So how in the world are we going to represent that? Well, what ends up happening, let's plot these, what I got, 5 points here. Let's plot these 5 points and see what ends up happening. Okay, so we have 5 points up here. If we plot them, I have the point x is 1, y is 3, x is 3, y is 1. What else I got? 2, 2, that's right about there. 5, negative 1's right about there. So if we take a look at those 4 points that we started with, all 4 of those were solutions. And if you notice, it appears that those look like they're falling along a line, and they actually are. However, the point that was not a solution, negative 2, negative 3, that's the point over here, x is negative 2, y is negative 3. Notice that that point is not on a line. So what we end up doing here is if we were to kind of project this, you end up getting a straight line. So here's the interesting thing. Since we have an infinite number of solutions to this equation, we actually can't write them all down. But amazingly enough, we can draw a picture of all the solutions. Because all the graph of an equation is a visual representation of all the points that are a solution to an equation. Let me get this up here for you, because this is a very important sentence. The graph of an equation is a visual representation of all the points that are a solution to the equation. That's all a graph is. It's just showing you a picture of all the solutions. So now notice over here from this graph, you can now use it to find more solutions, right? Here's a point of intersection, right? That's the point 4, 0. Notice that would also be a solution to this equation. Here's another oh, I wrote that wrong. Oh, backwards. It's a point 0, 4. Right? Also a solution. And down here, this is our point 4, 0. So there's easy to see 2 more solutions just from the picture of this graph. Now, this is true for any type of equation. Any type of equation, you can draw a picture of all the solutions. Now, the good news for us, the thing that we're going to learn today, the graph of a linear equation in 2 variables is a line. So this is where we all get kind of confused that linear means line, because there is a connection. If it's a linear equation in two variables, the picture of all the solutions is a line. But linear does not mean line in this case. So from this, we're going to see that it's going to be very important to be able to sketch the graph of these equations, in this case lines, so we can see what the answers are and how to represent our solutions. So we're going to take a look at how to graph lines in the future.